m bar, and Tm bar denotes its tangent bundle. On the tangent bundle, consider this function f with some hypotheses on it. First one is that f is homogeneous with degree 1 with respect to the normal, to this tangent vector field eta, and that f is convex with respect to this second variable 2. Choosing this f, you consider also an isometric immersion of remaining manifold M instead of this S is M. And given this isometric immersion, you could define this functional f, which acts on the position vector field, which is psi, and also on the normal vector field. It means that this functional depends on the position of the hypersurface and of the direction with respect to the tangent distribution of the hypersurface. Integrating this against the volume element induced by psi, you have this cursive f, calligraphical f. This is a geometric functional because f is homogeneous, so if you parameterize the hypersurface, you give the same number at the end. So this is a geometric functional. And the condition of convexity implies that the Euler-Lagrange equation is elliptic. This functional generalizes the notion of area. If you consider this particular choice of f, you have the area of the hypersurface, the volume of the hypersurface. If you add to the area this multiplier, you have area plus volume. So the critical points of this particular choice of f are the constant mean curvature hypersurfaces. Generalization of it is to consider, instead of h times this one form, you could consider this general Q expression. It's called Hildebrandt's functional. Another choice is to break the symmetry of the functional. So you choose this particular direction y, a particular vector field in the ambient, and you break symmetry, consider some perturbation of the area in this direction of y. This is this last choice. And you could complicate things to considering another functionals like this kind of Banach type norm. For example, immersion into a product of spaces. So, given this functional requires to derive a first versional formula for it. So, you first consider this cross section into the tangent bundle, the position of the hypersurface and the normal along the hypersurface, and you write along this section the first derivative of f. This, of course, is a vector field into the tangent bundle. You break this vector field into horizontal and vertical parts. You are using here, for example, the Sazak structure of the tangent bundle. It's one choice. So breaking the gradient into these two directions. Breaking the gradient into these two directions. I will pass this and I come back after. You could prove that the first variation formula of this functional, this means a kind of area, an isotropic area, this f, plus the volume. Lambda is a Lagrange multiplier, and the first variation formula for this reads like this formula. Xi and these two vector fields into 4 correspond to these two components of the gradient. This means the derivative of f with respect to the position and derivative of f with respect to the orientation of the hypersurface. So, fixed these two vector fields, the Euler-Lagrange equation is that one. It's a divergence type equation plus some extra term which has to be with the dependence of f with respect to the orientation. A particular choice of f is to suppose that f is horizontally constant. This means that F is covalently independent of the position. It depends only on the first entry. Sorry, on the second entry. This means it depends only on the position, on the vector, the normal vector field of the immersion, not on the position vector. This, for example, is the case of the area functional. So supposing this condition, the second vector field vanishes, and the Euler-Lagrange equation is just divergence of psi equals to this constant lambda. In this case of this last equation, with the second term on the left-hand side equals to 0, you could associate this psi, this vector field, psi, to a kind of anisotropic normal vector field, because the divergence of psi gives a constant. This constant has the interpretation of the anisotropic mean curvature. So this number lambda is obtained as a divergence of some vector field. This leads to this interpretation. Psi is the anisotropic version of the normal vector field in the case of horizontally constant functionals, where this second term vanishes. In fact, if you consider this case of horizontally constant Lagrangians, the derivative of psi generates a linear form, AF. This could be understood as an anisotropic Weingarten map in this context. The relationship between this anisotropic Weingarten map and the classical one is obtained by this multiplication. A on the right-hand side is the Weingarten map, the usual one. You multiply this by the Hessian of F, and you get the anisotropic Weingarten map on the left-hand side. So the entries, the anisotropic principal curvatures, are a kind of weight combination of the principal curvatures in the classical setting. The Hessian, in fact, is the Hessian constrained to the vertical distribution. We do not consider the derivatives with respect to the horizontal one. And it turns to be that this Hessian is a positive definite matrix. So the weights are all positive. And finally, we define this the trace of this anisotropic Weingarten map as the anisotropic mean curvature of the immersion. In the horizontally constant case, the mean curvature, the anisotropic mean curvature, is the divergence of that vector psi up to a sign. And in the general case, when you consider dependence with respect to the position vector field, instead of this constant mean curvature problem, you have a prescribed one. The mean curvature could be viewed as a prescribed function instead of a constant lambda. The classical example of solutions for it, in the case of Euclidean space, are the roof shapes. The roof shapes are convex bodies, are convex hypersurfaces, which plays the role of spheres in this theory. Instead of the sphere, consider this kind of ellipsoid, kind of a convex hypersurface, which is constructed by a very geometric device. You just consider the convex body generated by F. F is the support function which defines this convex body. The boundary of this convex body is the roof shape. And for the roof shape, the position vector is not, of course, in general, the normal position, the normal direction, but in terms of anisotropic setting, the position vector is again the anisotropic normal vector field. So the divergence of this is constant, and you get a constant mean curvature in terms of anisotropy. Another trivial example are the rotational hypersurface generated by symmetric invariant Lagrangians. In this second case, you consider a parallel vector field in M bar. For example, this could be the case of product spaces, Rn included. And you choose this particular Lagrangian. This term, the norm of eta, is the area, and you perturb this multiplying by this f. This f depends on the angle between the tangent plane, the tangent hyperplane of the hypersurface, in this particular direction given by y. So have area times angle, essentially. And this functional, thanks to the parallelism of y, this functional is horizontally constant. If you do the calculations using Sazak's metric, for example. And this function also permits to deduce flux formula for the hypersurfaces. This is this last expression, a kind of Minkowski formula. And these two ingredients, the fact that f is horizontally constant and that there is a conservation law for the hypersurfaces, permits to integrate the examples and to produce spheres, catenoids, onduloids, nodoids. All these classical examples could be reobtained by this consideration, by this choice of this particular functional. But this is a very trivial construction. A less trivial one is to consider graphs, avoiding the assumption that P is a model space. It's a space form. You could replace this by only considering P with a positive, non-negative rich curvature. And in this case, you could easily obtain the existence of graphs. You take a domain in this leaf P, in this totally geodesic hypersurface. Omega is open bounded domain with this boundary gamma. You take the cylinder over the boundary of omega. You suppose that this cylinder is a barrier in the sense that the cylinder has non-negative mean curvature in the anisotropic version of it. So the cylinder has anisotropic mean non-negative curvature. And if you choose h, sorry, this is not lambda, this is h. If you take this constant less than this ratio times hk, you could prove the existence of a graph with constant anisotropic mean curvature h. Again, it's not capital lambda, it's h. A confusion about letters here. So we have this graph with this constant mean curvature and boundary gamma. It's a trivial boundary. A boundary of the domain is the boundary of the graph. It's just a toy result for in this direction of more complex examples. In this statement, this mi corresponds to the eigenvalues of this Hessian matrix of F. In the case of that choice of F, which depends on this F, small f, the eigenvalues of the Hessian are given by this mi perp and these mi parallel numbers. These are the two eigenvalues of that particular choice of F, of capital F. Both of them are positive by the choice of small f. This theta is the angle between the hypersurface and the direction given by y, the vertical direction, say. For doing this, you use this kind of Kodazzi's equation for the anisotropic setting. This equation holds just for horizontally constant case. And using this Kodazzi equation, you get these two classical formulas in anisotropic terms. This is a kind of Laplacian of the height function, this 12. And the equation 13 is the Jacob's operator applied to the angle function. The Jacob's operator is essentially the second derivative of the functional f I defined at the beginning. So we have a Jacob field given by y, This is the content of this formula 13. And you have this Laplacian of height. And combine this in a usual way, you get a priori estimates, and then the graph exists by the fact that you get these estimates. These operators, L and nabla F, are modifications of the classical Laplace-Beltrame operator. The first one, nabla delta F, is the trace of the Hessian, but the Hessian with this weight given by the Hessian of F. So you get an elliptic operator, not with some anisotropy too. And this LU is a kind of principal part of the Laplacian. You took off this divergence of the Hessian. This operator remains to be elliptic too. Just to mention some non-existence result, which gives the idea that these techniques concerned with the Montreal principle and the weak versions of it could be applied also for this context. You also obtain this result in collaboration with Luis Alias and Marco Rigoli. It's the first one of maybe a series of results about non-existence, rigidity, stability, and characterization of graphs and hypersurfaces in general with constant anisotropic mean curvature. Just for mention that these techniques could be applied also for this anisotropic case. Well, continuing with existence results, you now replace the hypothesis that the ambient space has a parallel vector field. You replace this for the requirement that this vector field now is a killing vector field or a conformal killing vector field. You suppose for commodity that the distribution associated to y, orthogonal to y, is integrable. You fix integral leaf of this distribution, and you run the flow generated by y starting at this leaf P. You assume, for brevity also, that the flow is complete. And again, taking a domain in P and a function defined on this set, you could define the graph, the killing graph of U by this expression, by this M. And again, the fact that M has mean curvature, anisotropic mean curvature prescribed by some function H, and has prescribed boundary, could be viewed as the fact that U, the function U, solves a Dirichlet problem for some elliptic equation. I prefer to not present the equation, just the results. Of course, this is a quasi-linear equation, so it suffices to get C1 a priori estimates for it. This could be obtained by considering again the killing cylinders as barriers and choosing the correct choice of test functions in order to control the gradient and the height of the graph. And you obtain a result similar to the classical series result on the isotropic case. This was obtained by me and by myself and a student of mine, Flavio Cruz. And you consider, again, the killing cylinder over the boundary of omega. The cylinder has two notions of anisotropic mean curvature, one which refers to the inwards orientation, another one which refers to the outwards orientation. So you suppose that one of them is positive, the inwards anisotropic mean curvature is positive. You also suppose that the ambient satisfy this inequality, or from another point of view, that you choose this cylinder in the correct region of the space in order to get this inequality about involving Ricci and the mean curvature of the cylinder. Just a remark, this is not exactly the Ricci tensor, but the Ricci tensor And the trace is taken with respect to this Hessian matrix instead of the metric. And if h, the prescribed mean curvature function, satisfies this inequality, you could prove the existence of a graph with this mean curvature h and boundary, an arbitrary boundary data phi. This is a generalization of a result obtained earlier by myself, Marcus, and Nojosa. The main difference is that in the case of the isotropic result, you do not require the strict inequality in this last inequality. You could reach the extreme case of the equality. Some comments are in order. You could also think about the same, the analogous result for the case of conformal Killing vector field, as I mentioned before. And in fact, you obtained a partial result on the existence of graphs in the case of conformal Killing vector fields. The same result is part of a result which could give the existence of these graphs of some prescribed elementary symmetric function of the Weingarten map. This means that you could consider not only the mean curvature but another symmetric functions. For the time being, you just get the gradient estimates for it. It's necessary to also obtain C2 estimates in this case. This is in progress. I would like to also mention that these results for closed graphs, in particular for compact graphs, could be also obtained by using a parabolic method. You just design a flux which is given by the evolution of hypersurfaces with a speed given by difference between the anisotropic mean curvature and the prescribed function. This could be done also in the case of parabolic method. At least for the case of horizontally constant Lagrangians. Because in the case of horizontally constant Lagrangians, you could derive a kind of Simon's formula and to get a parabolic maximum principle for this flux. The result about the disclosed graphs in the elliptic setting is this one. This is a particular version of it in the case of Euclidean space. You consider now a graph with no boundary, a closed graph, lying between two spheres and the Euclidean space. The conditions about h are these three ones. It's likely that this third condition could be ruled out if you change the technique, but for the time being, it's the result you obtained for the case of Euclidean space. So again, you obtain the existence of a closed graph with prescribed mean curvature h. There are two inequalities. The first two inequalities involves the anisotropic mean curvature of the spheres. The graph is between these two spheres, and you consider these two spheres as barriers. So you should impose these two conditions, comparing the prescribed curvature function with the curvature constant of the spheres. Finally, I mentioned that our current goal is to establish the existence for these general elementary symmetric functions of the anisotropic Weingarten map. You have the isotropic version of this. The goal is to generalize a result I obtained with Flávio Cruz. This result in this isotropic case concerns the choice of some general function of the principal curvatures of the hypersurface, a function f. For our purposes, this f could be the sigma k function, or some root of this sigma k function. you choose a prescribed function given by this capital psi. The only restriction about psi is that one. And if you assume that the domain omega is convex, it's F convex, this means that this is convex with respect to this particular choice of this curvature function. And if the curvature of the graph and the curvature of the cylinder over the boundary gamma are related in this way, you could assure the existence of a graph with this prescribed curvature function, but this time assuming that there exists a viscosity subsolution of the problem. For the case of mean curvature, the domain itself is a solution, so we have no this problem. But for the another equations, the high-order curvatures, you are faced with nonlinear equations, full nonlinear equations, and you should assume that there exists this subsolution. You have no idea how to produce this automatically. So this result is isotropic, but our intention now is to get the anisotropic version of it. And this finishes my talk. Thank you very much.